Okay, so let's go ahead and get started. In today's lecture, we're going to talk about um, what's called the column space of a matrix. And the reason why we're going to talk about this abstract concept is that it is intertwined with a matrix having an inverse. And in the previous lecture, we were looking at computing the inverse of a matrix to solve a system of equations. So determining when a matrix has an inverse is an important thing to know. But to do that, we need a little bit of theory and abstraction. So let's start with the definition. So the space Rn, okay, consists of all column vectors with n components. Or with n elements. Okay, and we should be vaguely familiar with Rn, right? Because we've been playing around with n-dimensional vectors, and it's something that we're vaguely familiar with. But now we should think about it in terms of every possible point, like maybe visually even. So, for example, R2, of course, is this two-dimensional XY Cartesian plane, right? We're familiar with that. And every point in this plane, anywhere you pick, can be represented as a two-dimensional vector. Right? Maybe X naught, Y naught. Right? And in this space, we can add and subtract vectors from each other. We've done this before, right? In fact, we learned about this special combination, this linear combination of vectors. So when considering this, let's go back to this equation AX equals B. And let's choose now that, well, not even equal something. Let's just think about what that is, right? You should know by now that I'm a fan of the columns of a matrix when it comes to matrix vector multiplication, right? So this is like, x1 times the first column of the matrix, right? Plus x2 times the second column of the matrix, plus dot, 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 plus the nth column, so xn times a n, right? Those are just the columns of the matrix A. So this is a linear combination of the columns of A. So what exactly is happening here? Well, the matrix A has these columns, and these columns live in n-dimensional space, right? So when you take a vector x and you put it in here somewhere, let's say, let's call this x with components x1, x2. When we multiply x by a, it's going to transform, but maybe I should just say this is going to be equal to some vector b, right? So what this matrix A is doing is it's taking x and it's moving it to another vector b somewhere in this space, okay? And the columns of that matrix determine where x gets moved to, right? And some funny things can happen. Not funny. We should be aware of certain properties of the columns of A. And by that, I mean, we should probably look at a specific example. So, for example, if A is equal to 1, 0, 2, 0. Okay. Make sure you can read that. So suppose this is your matrix, right? And let's say that this vector here is equal to, I don't know, what does it look like? Maybe like 5, 3 or something. So can any of you guess what's going to happen when we multiply this matrix, this matrix by that vector? Like, what is this matrix going to do to that vector? Can anyone guess? Like, where is it going to move this vector? Currently, it's right there, right? And then we're going to multiply it by this, and then where is it going to go?
Up and to the right.
Well, let's see. So then, 1, 0, 2, 0 times 5, 3. This is just going to be the vector what? 5 times this column plus 3 times this column. So it'll be 11, 0, right?
Yeah.
So 11, 0 would be like, it'll move it to like there. This is like AX. Like right there. What about if we multiply another vector? Like suppose we have like, we'll call this vector like Q or something, Q. And maybe that's like -3, +2. Where do you think this matrix is going to move that vector to when we multiply? Where is it going to land? Well, we can look. So then, what is it? So we have 1, 0, 2, 0 times -3, 2. So, okay, this is going to be the vector -3 plus 4, so it's 1, 0. So then it'll land like right here. A times Q. Can you guess what's going to happen if I take another vector? Maybe like there. And I multiply that vector by A. What's going to happen?
It's going to move to the x-axis.
Exactly. In fact, every single one of any vector you pick and then multiply it by A, it's going to put it on the x-axis. So no matter what we pick, right? So it seems to be in this case that the space of all vectors that A will move to, they will all lie on the x-axis. So in this case, we're going to say that AX spans R1. The space of all possible vectors is exactly the real R1. It's just this x-axis. Do you see that? Like, that's kind of a special thing, right? Like, for some reason, this matrix always puts me on the x-axis. What is this reason? Let's choose a different A now. Let's choose A to be 1, 2, and 4. No, just do 2, 4. So what about this matrix? Let's see what happens now. Okay, so our first vector is 5, 3. So 5, 3 was like right there. This was like x. So let's see what happens now. So 1, 2, 2, 4 times 5, 3. So what is this? It's going to be 5. So this is like saying, I'm just going to write it out to be safe. 5, 10 plus 6, 12. So that's going to be what? 11, 22. So 11, 22, it's like way up here, right? So maybe I'll just erase this definition. So it's like, that's 5, it's like probably way up here. Something like that. Okay. What about when we multiply -3, 2? So this is like -3, -6 plus 4, 8. So this is going to be 1, 2. Yeah, 1, 2. 1, 2. So it's like right there. So this is A times Q or whatever. And this was A times X. And Q originally was like, what was it? Negative, no, it was -3, 2. So like, right there. That was like Q. What do you think? What was the other one we multiplied by? Let's just pick another one. Let's say like Z is going to be 1, -1. 1, -1. So what do you think this is going to go to? 1, 2, 2, 4 times 1, -1. So this is like that minus that, basically, right? So this is going to be 1 minus 2 there, and 2 minus 1 there. -1, 2. -1, -2. -1, -2. Oh. So that's A times Z. Do you notice a pattern? Where are all of those vectors landing?
What?
They're landing on this line. Right? They're all on that line. Why is that? It's not always the case that that happens by any means. Like, this is kind of special for some reason, right? And in fact, what do we like this? There are some special properties of this line. So let's say, so anyway, let S be the space of all vectors, space of all space. You don't know exactly what space means yet, but we'll get there. Of all vectors obtained by, what was it, 1, 2, 2, 4 times x. They'll all be on that line. And what's interesting about this line now, if you're on that line, is that if you pick any vector on this line and you add another vector on that line, you're going to get a vector on that line. So if x and y are in S, so for things to note, x in S and y in S imply x plus y is in S. Because if you add any vectors, they're going to be on that line. And 2, x in S implies c times x is in S for any scalar c. Right? If I just pick a vector on here and multiply it by c, it's just going to get longer and stay in that line. Okay? Also, number 3, the 0 vector is in S. So this is what we call a subspace. So S is a subspace of R2 because it satisfies these 3 properties. Now, it spans only one dimension, basically. Everything lies on a line, where the full space is a big plane. Okay. So this is special, and there's a reason why we're all landing on this line. Can anyone guess why? Like here we all land on a line, the x-axis, if we multiply by that. With this matrix, we also land on a line, just this one. What do these have in common? Anybody? Anybody? What do they have in common?
They have a 1 in the first entry.
Oh, that is, they do have a 1 in the first entry. What else? And that's actually, it actually wouldn't matter. For example, if I made this like if that was a 2, that's still fine. And if I made that like, if I made this like a 3 and this is 6, it would still be 5. You would still land on a line. So why am I pointing this out? Why am I so concerned about landing on a line and not in the space all around it? The reason why I'm concerned is this. I'm concerned because we want to solve systems of equations. Systems of equations look like this. You want to solve that. However, what is AX? AX is a linear combination of the columns of A. So the space of all possibilities here, if A was one of these matrices like that, like 3, 6, 2, 4, or whatever, or the one I had before, what was it, 2, right? So like, if we looked at 1, 2, 2, 4, and we wanted to find a vector x1, x2, that equals, I don't know, 1, 4. Can we solve that system of equations? Can we solve for these variables with that matrix? Just looking at the picture.
No, because it's not going to fall on that line.
Exactly. Exactly. Because that B vector is like 1, 4. There's B. And B is not in the space spanned by that matrix A, right? Matrix A made all multiplications by A landed here, but B is like way over here. Has no, so this has no solution. You can't solve it. So this brings me to an important concept, a definition. The column space of A consists of all linear combinations of the columns of A. Okay, so that's the column space. And if the vector B does not belong to the column space of A, then you can't solve it. There is no solution when that's the case. But again, how do we know that we're landing on a line and not all of the space when multiplying by A? Well, it turns out, well, I think I have a better way to say it. Let's consider this, right? Let's consider this equation, the special equation. Okay. And we ask ourselves, what are the solutions to this? Right? Like, what are the possible solutions to this? This is remember, this is the zero vector, right? Right there, zero vector on the origin. Right? So, what if there are non-zero solutions to this? And what if you can add these columns together to land here? And so this is like x1 times the first column plus the usual notation here. So I guess I'll just give the definition now. The columns of A are called linearly independent if the only solution to this equation is the zero vector. Nope, vector. Okay. So linearly independent. Okay. So let's go back and look at this matrix A that we've been playing with, this 1, 2, 2, 4 matrix. And let's look at this equation. Does that have a solution?
Yes.
What's the solution?
It'd be 2, -1.
2, -1. Okay. That works, right? 2 times the first column minus the second column gives you 0, 0. So these are not linearly independent. What was the other matrix we had? It was 1, 0, 2, 0. Does this have a solution? A non-zero solution?
You can use 2, -1 again.
Oh yeah, that's a solution for that one as well. That's just a coincidence, but do you see in both cases they are not linearly independent? So these columns are called linearly dependent. Because there is a non-zero solution to that equation. So when you think about it, why does this make sense? Why would this be the case that what's going on here? Why is there a linkage between landing on a line and having linearly dependent columns? The linkage is this. Where is the vector, the column vector 1, 2? I'm going to put it in blue. 1, 2. So 1, 2. There's a 1 right there. Where's the other column? 2, 4. I'll put it in like yellow. 2, 4. Look at what's happening here. There is a solution to this because that column is a multiple of the other column. That column is a multiple of this column. And what happens when we multiply that matrix by x? We're taking a multiple of this column plus a multiple of the other column. Where could you possibly land? It has to be on a line. right? It's not gonna, it can't move anywhere off that line. If we have both columns here, right? Then if we take any addition via scalar multiplication, any linear combination, we're just gonna be like up, 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 all on that line. So one way of testing if that's going to be the case is linear independence dependence. If the columns are linearly dependent, they're all on the same space. They're stuck on this space, a subspace of the larger space. Okay. And when that's the case, we have to worry about vectors that aren't on that space. Okay. So hopefully now you see why this might be important to think about this geometrically. That the column space, if you're trying to solve in general for B, there's so many different solutions. But if you're restricted to a single line, that's bad. Right? So it also turns out that linear independence corresponds to a matrix being invertible. Because, well, why is that? Well, if the columns are linearly independent, if they're linearly independent, then think about it in space. So this was like the bad case, linearly dependent. All in that, the columns all lie in the same subspace that's a R2 on that line. So when we take linear combinations of the columns, we're always on there. So there's going to be all types of vectors where this will not have a solution. Okay. Now let's consider the good case. So just so I don't forget, this was 1, 2, 2, 4. That space there, stand by that matrix. Okay. So if the columns of the matrix are not all on the same plane, right? So for example, let's say, so for this matrix here, those were the two, so this is like A1, this is A2. Maybe I'll make a new matrix now called Q. Maybe Q is equal to 1, 3, and then maybe like, or maybe I'll get rid of that 1. I'll do like a 2, 3, and then maybe like a 2, 6. No, 2. It doesn't matter. Like whatever. 2, 1. Yeah. So now, when I draw the columns of Q, I have 2, 3, and 2, 1. Let's make it like a little bit more drastic. Let's say 2, negative 2, negative 1. Now, when we look at these columns, right? When we look at these columns, we see that, oh, if we add them together, right, we can get pretty much anywhere. Like suppose if I subtracted that off of that, I could land right there if I wanted to. If I, if I wanted to get there, right, maybe I could just like scale that one back this way and then point it there. And, like subtract that and then add that. In all of the possible linear combinations of these two columns, all of that's going to end up every possible point, because they're not restricted to a single dimension. When you start adding and subtracting and multiplying them, every possible combination you can think of, you start to hit all of R2. So in this case, we would say the column space of Q spans R2. Okay. Okay. So this is in two-dimension space. I should also say that the notation for the column space of a matrix C A. That's the column space. Okay, and all of the solutions to this equation here, AX equals 0, the solutions are given by the null space. The null space of A. I should have said that earlier. Okay. So there's these, they're both vector spaces. They're spaces of vectors that contain 0 vectors. So, so the column space of this matrix happens to be everything. The column space of this matrix happens to be just these, the line and the line. And when, so to like determine, to introduce terminology to make things simpler, we'll say the rank of the matrix. And we'll get to that definition shortly. There's lots of definitions coming, but hopefully this makes sense that when solving systems of equations, we kind of want, we most definitely want the matrix, the matrix with n columns to span n-dimensional space. If that's the case, then we're good. Okay. Okay. So, let's see. Oh, I should probably say one more thing about the picture here. These two columns, the only way to get them to the 0 vector is to multiply them by 0. Because they don't live on the same line in this case. You won't be able to add and subtract them to get to the 0 vectors. It's impossible. Okay. But now this is R2. This holds generally for Rn. So this is going to be very difficult for me to draw. But I'm going to try my best. So x1, x2, x3. So let's see what happens when we have a matrix, maybe. Are the columns of that matrix linearly independent or dependent?
They're independent.
They're dependent. They're dependent because that column is a multiple of that column, and that column is a multiple of that column. But it only took, like, for example, let me make this a little bit different. Let's say,
Well, wait, is the last column a multiple of the first?
yes. 1. I could do 2, 4. Oh, yeah, that works. So now these columns are also linearly dependent. Why? Because does this have a solution? 2. Well, you know what I'm about to write. I'm running out of room. Basically, 1 times that plus 1 times that minus that is equal to the 0 vector. They're dependent. Okay, and where do they live? So like 1, 1, 2, 1. So maybe I'll make it a little bit bigger. It's like there. It's like 1 vector. It's that column, and then 1, 2 over 4 up 1. Oh, up 1, I see. There. And then 3, 6, 2. So 1, 2, 3, 6, maybe this way, 2. It's like over here somewhere. You can't see it with this picture, but really what's happening here is that all of these vectors are all of those vectors live on a plane, a single plane in R3. It's hard to see, but there's a flat surface in here, and that all of those vectors are on that flat surface, which means that any combination of them will also be somewhere on this surface. Which is bad when trying to solve systems of equations because, well, what if there's a vector that's like way up here? What if B is right there? Then we can't get to it, right? We cannot get to it. So because they're linearly dependent, which means that they're multiples or they're of each other's in some sense, right? They all lie in the same subspace, which is not the full space, okay? So we would say that this, the column space of this matrix does not span R3, okay? And is it time to give you the definition yet? Almost time to give the definition. Okay, so now to the important point. Important thing is that if they all did not lie on the same plane, if they were linearly independent, then they would span the space. If they span the full space, then any vector anywhere, if you span the full space, you can get to it by multiplying by A. So AX equals B always has a solution when the columns of A are linearly independent. Which means, which is important to us, because this will tell us that A inverse exists. We can always find the inverse when the columns are linearly independent. So recall the properties of the inverse, that A inverse times A is equal to the identity matrix. And A times A inverse is equal to the identity matrix. And the identity matrix is the matrix with ones on the diagonal. And because of that, when we have a system of equations that looks like that, and the columns of A are linearly independent, we know that the inverse exists. So we can go about trying to find that inverse. And once we do, we just multiply both sides of this equation by the inverse. A times A inverse is just the identity. And identity times X is just X. So when the columns are linearly independent, we can find the inverse by multiplying the equation by these matrices like we did last time. This is equivalent to what you might have seen before as row operations, because we're modifying the rows, we're also modifying the other vector. Once we find the inverse, we find the solution. Okay. One note on the inverse about inverse of products in matrices, because this happens a lot. You want to take the inverse of a product of matrices. This is going to be B inverse times A inverse. The order does matter with matrix multiplication. Please never forget that. Okay. So I think I'm going to go ahead and stop this recording because this, I think, illustrates the points I needed for the columns of A. Okay.